And as I have already demonstrated that the spline option is the best provided in the one-dimensional or two-dimensional figure. So let's have a further look in spline functions, and I will explain something about spline later. So spline interpolation is very useful in data interpolations. So what are splines? Splines are a set of basic functions, and from it we can perform a more complicated function either by linear combination of spline functions or even more complicated functions. And I will explain splines in some examples later. And I will explain something about how to solve spline interpolation problems first, and then based on spline interpolation I will explain how can we perform numerical differentiation and numerical integration from the simple points, which are different from the theoretical theoretical differentiation and integration. So let's consider spline interpolation first. And there are usually two kinds of useful spline functions. One is called cubic splines. And it should be a piecewise cubic functions. And the other one is the B-spline, which are quite useful in approximating the data types. So I will explain in detail how we can solve these problems using Matlab command. How can we construct a spline object and how to use it. So let's consider cubic splines. And this is mathematical details about the definition of cubic spline. For instance, we have a set of data like this, and in each interval we will approximate the function in this interval by a cubic function like this. And each interval has a cubic function, but the cubic functions may be different from intervals. And the conditions we must satisfy, the cubic functions must satisfy are as this. This should be continuous at the sample points. So we may have different cubic functions in different intervals, but the function value at the sample point should be the same. And also they should be the derivative of them up to the second order derivative of them also should be the same. So it seems to be quite difficult to find the cubic functions. So do not worry about it. We can talk about how to find this function with the usual method. If you have already a set of data x and y, you can create a cubic spline object using a command like this, where S is an object. So if you have data, you can use this command to create an S object. And then you can perform, you can draw the plots, and you can also perform interpolations with Fn val function. I will explain this through examples later. And let's go back to the example again. We have already demonstrated this example earlier. In this example again, we should first generate two sets of data, the set of data of x, and then we can calculate from the function to find the y values. And from this value, x and y vectors, we can create a spline object. The spline object name is ST. this is the spline object, ST. From the spline object, we can use FNPLT to draw the spline interpolation result. We do not have to specify the value of X as the interpolation point. We can easily draw the spline fitting of this one, like this. It should be very close to the original X, original or theoretical curve. I think you still remember the theoretical curve. It should be the same. So this is the result of cubic splines. Cubic spline explain interpolation results. Let's see what information the spline object contains. First, the form of the spline, which is called PT, which is piecewise cubic function, cubic spline. I'm not quite sure what it stands for. The bricks, we can show the bricks then. ST dot bricks, which are the points of given measured data or sample data, 0, 0.12, and 0.24, because I used the incremental 0.12. So these are the sample points actually. The argument brick returns the sample point of X. ST. Apart from the bricks, we can also have coefficients, and we can display the coefficients ST dot COESS. And these are the coefficients, and I will explain it like this. For the first row of the data, which are the coefficients of the polynomial, of the cubic polynomial, is for the first interval from 0 to 0.12, and these are the coefficients for the second polynomial in the interval of 0.12 to 0.24. So we can have, in each interval we will have a cubic function, and these are the coefficients in each of the functions, in each of the intervals. And for instance, we can have in the fourth interval, the fourth interval should be from this is the fourth interval, and from the data we can easily construct the polynomial in this interval like this. X minus 0.36 cubed plus from the coefficient we can easily reconstruct the polynomials in each interval. So these are the data obtained using Matlab commands. And also we have pieces and order and dimension, one dimension. By using a simple command like this,